So I begin by, this is the outline of my talk. I'll begin by explaining what single chain nanoparticles are, and I'll explain why understanding their morphology is important in the first place. Then I will talk about two ways in which we try to tune their morphology for various applications. Then this phase behavior of SENPs is something that I recently started working at VIT with a master's student. So I'm going to share those results and conclude. So what are single chain nanoparticles? So imagine a polymer chain like this having this special monomers. You can call them as reactive monomers. So using external triggers like pH or temperature or light, we can make these monomers cross-link with each other. So the nature of cross-linking is of different types. It can be irreversible or reversible. So when we speak of irreversible, it's obviously the covalent bonding. And in reversible, we have a toolkit of different interactions that can form these crosslinks. And this folded nanoparticle is of the sizes, the typically experimentally synthesized nanoparticles are of the sizes of 3 to 30 nanometers. So, and because of the tunability of this internal morphology, they have a wide range of applications in drug delivery, catalysis, and so on. So another interesting aspect of studying SENPs is their biological relevance. So if, for example, if you solvate this SENP in a good solvent, then the aggregation of these monomers makes them form this kind of extended configurations or sparse SENPs. So experimentally, people can study their structures, and when you match their form factors, they are similar to intrinsically disordered proteins. Similarly, the globular morphology can serve as a model for mimicking enzymes. So they have these biological relevances, and these are different interactions which I just spoke about. They can be pi-pi stacking, hydrophobic interactions, or it can be of this heterotypic associations also, where you have these crosslinks formed between two different chains, not intra, but between two different chains and so on. So with this sort of general introduction, I'll go to the first problem of my talk, where we try to study the self-assembly, basically, or you can say autonomous folding of a amphiphilic random copolymer made of these OEGMA and IMA units. Okay, so in principle, if you solvate it in a selective solvent like water, it should form core shell type of architectures in principle. Like I said, this nanoparticle has applications in drug delivery. So there, the type of morphology that we need is globular in nature. So we need to understand what parameters can tune its morphology to be globular or sparse in the first place. So which is why we take the help of simulations here to understand the morphology microscopically. So to give you a brief idea of simulation techniques, already in the morning sessions, Debanjan explained us about coarse-grained force field and so on. So depending on the length and time scales that we are interested in, there are different simulation techniques people use. So here we were interested in the nanometer and nanosecond time scales, length and time scale. So we basically went to atomistic MD, and so someone who is working in MD already know these are the packages that we use and so on. So for this particular project, we used amber force field, general amber force field and amber package. So here is the basic framework. I don't want to go into details because the audience already know, I believe. So firstly, we build the model where we assign different coordinates and velocities for all the particles in the system. Then we define the force field. In the molecular degrees of freedom, we have this bond, non-bonded interactions sitting here, and then we update the positions and velocities through numerical integration and so on. So this is the basic framework of molecular dynamic simulations. If anyone has more specific question here, I can talk. And going into the problem, so we took the hydrophilic and hydrophobic entities from the experimental group working at so this work has been done at Spain, San Sebastian. So there is an experimental group who were interested in studying the folding of this polymer, and the specific molecular weight and the units, everything is taken from there. Okay, so these are the units of hydrophilic and hydrophobic entities, and this is how we build the polymer. So we define a head group basically, and let's say the second entity has head as well as tail. So the head of this is connected to this and so on. So there is a way to program this in XLeap if someone is interested. So this is how we can build the entire polymer chain. And after solvating in water, this is how it looks like. So the system sizes that we typically took were of this order. And with the computational facility we had then, it took about 10 nanoseconds per day for the simulations to run. And we also were interested in what is the structure of this polymer if we make crosslinks. I'll come back to this. But in XLeap there is a way to even crosslink the units. So you can define again head and tail and make a crosslink between them with a different entity, which is basically ethylene diamine here. So I'm just kind of showcasing what Amber package can do basically. Okay, so we have built our systems in this way, and we basically followed this strategy to see if we can generate an intrinsically globular SENP. So that was the motivation. Okay, let me go back to this slide. So typically when these nanoparticles are synthesized, people use good solvents like THF. So there the conformations are always sparse in nature. But like I said, for catalysis or drug delivery, you need a globular morphology. So we need strategies which can help us get such globular morphologies. So that was one of the motivations for doing this work. So here is the design principle we followed to see whether we can get a globular morphology basically. So firstly we took the polymer precursor and solvated in water, and then which is a selective solvent because we have both hydrophilic and hydrophobic units in our polymer. And then we solvated this structure in THF, and then made crosslinks and did the same. So I'll come back to this when I explain the results. Already in experiments people followed this protocol. Let's focus on protocol 2 here. So what they did is they took a polymer precursor and used metal ligand coordination as the crosslinking what should I say, action. And when they solvated in water, they formed this kind of globular morphology. So this is just a schematic. We can also confirm them by this form factor exponents here. So you can see when the precursor is there, its exponent is 0.59, which is close to the polymer's structure in good solvent, right? And when we follow this protocol 2, you can recover 0.48. So it is kind of forming a compact morphology. So in experiments, we have some evidence that if you follow this kind of protocol where you first solvate the polymer in a selective solvent and then shift it to a good solvent, you can achieve a compact morphology. So we had this idea from the experiments. So then we wanted to test the same in the simulation. So I'll show you the equilibrium movies of the simulations, and I'll let you observe for a minute. So here OEGMA is the hydrophilic unit, IMA is the hydrophobic unit. Okay, so these are the simulation movies of about 200 nanoseconds. So here you see the structure in water, and here you see it in THF, which is a good solvent. So what you see is that as the simulation progresses, in THF the structure opens up, right, as compared to water. We will also quantify these observations, but from the simulations, what we observe is this. Sorry, yeah. So from the simulation snapshots or movies, what you observe is that in water the morphology looks a bit compact as compared to THF. We see extended conformations here. So that is the observation right now. We will be quantifying them in a minute. And we also looked at what is the impact of cross-linking of these hydrophobic units. So which is how experiments also do the cross-linking. When they use this kind of metal ligand coordination, so when they use this kind of metal ligand coordination, the crosslinks form between the hydrophobic groups. Okay, so although in the simulations we didn't use metal ligand coordination, we used ethylene diamine to model the crosslinks basically. And it is between the IMA units, which are the hydrophobic units. So what we see from these movies is that The structures seem to remain compact in both water as well as THF. Let's look, I mean, it's not very clear from the movies what is happening after we cross-link, but we can understand them from the basic measure of the size of the polymer, which is the radius of gyration. So you can see in THF consistently the structure has higher size as compared to that in water. Okay, so this is with cross-links and this is without cross-links. So what we do see is that when we have cross-linking, the increase in the size is not as much as the other case. So in other words, we can say that the structure is retaining its internal architecture and swelling. To understand or confirm what I just said, we looked at the form factor profiles again, and in the fractal regime you can see in THF it is forming an extended conformation because the exponent is 0.6, and when you shift it to water, when you solvate it in water, it is 0.26. So which is confirming that the polymer is forming a compact morphology. And when you have cross-links, the exponents are not very different, whereas you see some slight increment in the size. So it means that the polymer is retaining its internal architecture and it is swelling when you transfer it to THF from water. So this is an important application when we think of drug delivery. So you can prepare this polymer in water and load the drug and transfer it into a better solvent, which is THF, and in that process it swells and releases the drug. I mean, this is just a potentiality that we are expecting with this output. And if you want to compare the exponents with the experiments, the comparison is not exact. I mean, you can see the exponent here, which is, let's say you are comparing protocol 2 with THF crosslinks. That is the exact comparison. You can see it's not matching accurately, but this could be because of various reasons. I mean, we simply have one polymer chain solvated in water, so we can improve the statistics by choosing different initial configurations and so on, so which is something that we are trying to understand better. But the important implication coming from this study is that in THF the structures are swollen or extended as compared to that in water. So then we also try to look at what is the distribution of these hydrophilic and hydrophobic monomers from the center of mass of the polymer chain. So you can see that the hydrophilic groups are outside. I mean, in other words, you can say that the hydrophilic and phobic groups are forming core shell kind of architecture, because you see the density of this phobic groups is more at the center of mass in both what should I say, in both water as well as THF. Okay, so these are the data for the non-cross-linked case, and these are the data for the cross-linked case. Here you can see the density to be even more, right? So the core shell architectures are more pronounced in the cross-linked case, and our force field parameters, whatever we have chosen, are able to explain the expected behavior, okay? So this is the conclusion from the first part. And in the second part, we were interested in looking at dynamic covalent networks of polymers. So if you have polymer chains, so imagine these SENPs put up in a box, so several SENPs, and let's say the interaction between these crosslinks is reversible in nature. So like Khushbu already discussed in her talk, there is a formation of networks and so on, right? So similarly here also you can think of having such networks. So the mechanism of formation of these networks can be associative or dissociative. So in dissociative, what happens is that this crosslink breaks first, so there is loss in the structural integrity, and then it forms another crosslink. So these kind of models describe thermoplastics better, and these type of models where you have first an association and then a shift in the crosslink, these models are more suitable for Witt-Riemer kind of systems where you have the crosslink density to be constant. So our idea when we started this work was to understand, can we model these reversible gels with molecular dynamic simulations to understand the associative CAN mechanism basically. So to maintain the uniformity of the talk, I am not going to discuss the networks. aspect, but I'll discuss the structural aspects of these SCNPs where we have studied them at high dilution limits. Okay, so this is our model. So it's the basic polymer Kremer-Grest bead spring model. So what you see here is that these yellow monomers are the reactive monomers. In the sense, if there are two reactive monomers or these yellow beads within a defined capture radius, they can form a crosslink. So that is our model, and the bead size here is of the order of Kuhn length. It is the length at which the polymer segment is flexible in some sense. And to model the chain connectivity, we used Fene, and to model the non-bonded interactions or the excluded volume interactions between the beads, WCA we have used. So if you combine these two potentials, this is how it looks like. So there is a minima at about 0.96 sigma, okay? So the chains, the beads cannot cross each other basically beyond 0.96 sigma. And the important thing that I said is reversibility. How do we model reversible interactions? So for that we used a 3-body potential which was given by this Sotino group, Sotino and co-workers. So this is a Stillinger-Weber kind of potential, and if you plot it, it looks something like this. Okay, so there is a distance at which this potential is minimum, and beyond that this is how it looks like. So the 3-body potential is defined by using this Stillinger-Weber potential, and it looks like this. So it gives a repulsive interaction beyond 1 sigma. So what is exactly happening is, let's say there is a bond between A and B reactive monomers, and let's say another reactive monomer C is entering this. So what ideally we want to achieve is a bond swap, something like this. So to do that, we impose an additional repulsive potential through this 3-body potential. So whenever this triplet is formed, there is a energy penalty that we need to pay. So in that process, the system minimizes and forms this, makes this bond swap basically. So our bond swapping is through the Hamiltonian of the system basically, and so these are the model details. And what we were specifically interested in is dual dynamic cross-linking. So let me explain what I mean by that. So imagine a chemistry like this where you have reversible interactions happening between two different chemistries. So one is through disulfide bonds and another is through, let's say, acyl hydrogen bonds. So similarly, you can have this type of variety where you have this acyl hydrogen and hydrogen bonding also. So there are many ways you can form this dual cross-linking. So what is the advantage of having such a cross-linking? So this is an experimental work where they look at the stress relaxation times of disulfide Wittremer ester and a dual dynamic Wittremer, which consists of both this disulfide and ester. So across various temperatures, you see that when you have a dual dynamic Wittremer, consistently the stress relaxation times are lesser. So you can use this orthogonal chemistry or dual cross-linking to achieve better mechanical properties, or in other words, you can tune the viscoelasticity of the network. So with that motivation, we took the chain to be of this form. So it's the same Kremer-Grest bead spring model. The only difference is we have now two types of reversible interactions, AA and BB. So we don't allow the cross interactions AB, but we do allow AA and BB. And to understand the relative influence of the bond strength, we make one of them to be stronger as compared to the other. So let me show you where this bond strength enters the model. So this epsilon sigma SS that you see, which is precisely this depth, is nothing but the bond strength of the reversible bond. And we chose it to be about 12 kBt, 12 to 17 kBt in our model, so which is much higher than the thermal energy. So for the parameters that we have taken, we have about 0.9 as the bonding probability. So almost all bonds are formed in our system. So I have not explained this fraction here, F. So F is the fraction of reactive monomers. So we have about 200 beads monomers in the chain, and about 60 of them are reactive. So with such fraction, we are able to achieve the highest possible bonding probabilities. So we needed it because, like I said, our motivation was to model Wittremers where the cross-linking density was constant. So when you have such higher probability, bonding probability, it means that you are maintaining the same value throughout the simulation. So in some way, we are able to mimic the Wittremers system. So which is why we chose these kind of parameters, okay? So then let me go through the results part. So we varied this fraction of reactive monomers. So Na, so we have a total of 60 reactive monomers, out of which some we are choosing as A type and some we are choosing as B type. So we are systematically changing the composition of A monomers, let's say, and these are the typical reversible bond energy parameters we have chosen, and different, our idea was also to study the influence of the monomer sequence. So like I am showing here, this A and B can be arranged randomly or in a die block fashion like this, where the first half of the chain is only composed of A type beads and B type beads. So we will see how such small variations in the composition can lead to macroscopically different properties. Okay, since I am interested in the formation of SENP, single chain nanoparticle, so most of the results that I am showing you today are in this limit, infinite dilution. So in simulations, if you are interested how you model such a thing, basically we avoid intermolecular interactions between the chains. So that is, in other words, saying that the chains are not seeing each other and they are at a high dilution limit and so on. So if you look at the basic quantification of the size of the chains. So there is clearly a non-monotonicity in the size as a function of the composition of the reactive monomers. And what you see here is something very interesting. So if you take a pure A system where you have all of these beads to be made of A type, singly, you can say homogeneous cross-linking. So in that case, the size is almost you can see it's 9.25 or so, but here the sizes are very less. So what is exactly happening here is that, so when you have different types of reactive monomers, you are increasing their contour distance. So what do I mean by that? So let's say this is the backbone of the polymer, okay? And if I'm saying ith monomer is bonding with jth monomer, so I can define a parameter like this S, which is the contour distance, which is nothing but the magnitude of the difference between their indices. So if you look at the histogram of such contour distance profiles, so this is how it looks like. So what you see here is that for x is equal to 0.5, the long range loops are relatively more. Right, so you can see the magnitude of this red beads here is slightly more as compared to the other two cases. So why is that happening? So in x is equal to 0.5, let me show you how many reactive monomers we have. So this belongs to x is equal to 0.5. So a given type of reactive monomers which can form bonds is only 30 here, whereas in the other two cases it's 50, right? So in this case, to see the monomers of the same type, they have to form a long range loop as compared to the other two cases. So any question? Okay. So in the other two cases, simply because the number of majority species is more, they can see each other at shorter contour distances, and so their probability of forming this short range loops is better as compared to x is equal to 0.5. So in some sense that is leading to this non-monotonicity that we observe here. So because this x is equal to 0.5 case is involving in long range loops, it is having shorter size, lesser size. So there are two ways to now make compact SENPs. One is you simply increase the number of reactive beads along the polymer chain so that the distances of these pairing increases, and the other thing is, so that is what basically is orthogonal cross-linking, and the other thing is you can play with the composition of these monomers forming the bonds. So the lesser they are, the more compact your structure is. basically. So those are the implications coming from this microscopic study. And we also looked at what is the internal structure or the nature of conformations of these polymer chains. So as compared to the pure case, which is x is equal to 1, the form factor exponent here is 0.6. But when you are in dual cross-linking limit, you see it to be 0.46. So clearly, we can form more compact structures with dual cross-linking. And we don't see much difference when we change this bond energy disparity. So like I said, we chose different parameters for the reversible bond interaction strength. So even when you change it from 1215 to 1017, we don't see much difference in the conformations. But we do see some differences in the dynamical properties like MSD and viscoelasticity and so on, but I'm not discussing them in this talk. So yeah, these are the conclusions coming from this part, where we see that orthogonal cross-linking indeed leads to more compact structures. So we are always talking about rho tending to zero limit here. And so we don't see any dependence on the structural conformations with respect to the composition as well as the bond energy disparity. So you may ask the question, so I just discussed the scenario at infinite dilution. You may ask the question, what happens when you go for higher concentrations? So you can see the Rg is not changing that much. The size of the changes is not perturbed as much, and you can also find the conformations to be unperturbed basically. So which is not true if you are talking about irreversibly cross-linked chains or simply linear polymers. So if you are keeping them in a melt at higher crowding, there will be some shrinkages seen. So, but in this kind of reversible polymer networks, the shrinkage is not seen because of the formation of intermolecular bonds. So there is a gain in combinatorial entropy. I'm going to discuss in a minute about it. So, in my group, based on this result, basically, so what it is implying is that the many body effects can be neglected. Even though you are at higher concentrations, the molecular conformations are not perturbed. So it means that you can neglect the many body effects and use simply the pair interaction potentials to describe the supramolecular organization at higher density. So this was needed to reduce the computational cost. So for example, you can find the interaction potentials of simply 2 single chain nanoparticles and use that potential in a high density system or supramolecular organization. Yeah, so if you are interested, you can have a look at these papers. So far I have discussed the consequences of orthogonal cross-linking and the influence of monomer composition. But what happens if I change the distribution of these monomers? So in this case, I have randomly distributed A and B monomers, and in this case, they are arranged in a die-block fashion. So what you see is that there is a drastic difference in the form factor exponent. So you can basically, in symmetric case, there is extended conformation. So why is it happening? So you can understand it from again the contour distance distributions. So in symmetric case, if the A-type monomers have to find each other, they can only form these local aggregations. They cannot form long-ranged loops. It is prohibited structurally. Whereas in random case, such long-range loops are possible, so which is also evident in these profiles. So at higher contour distances, you see in the symmetric case, the probability is less, right? So because of that, the structures are forming extended conformations in symmetric case. So this is the summary coming from this part. So simply by tuning the arrangement of the reactive monomers, we can achieve different conformations. So I will also show the results for higher densities. So, okay. So you can see as we go for higher densities, the formation of intermolecular bonds. So the dashed curves here are basically intermolecular bonds. Sorry, I didn't put a legend. But you can see in random case, the probability of formation of intermolecular bonds is higher than in the symmetric case. So what is happening in random case is that a long range loop is getting exchanged with a intermolecular bond. So why is that helpful? So there is a gain in combinatorial entropy. So imagine arrangement like this. So for example, if A and B were to form an intramolecular bond, there are only two ways that can happen here, A, B and C, D. But if A were to participate in intermolecular bonds, there are many possible arrangements. So the system wants to enhance the combinatorial entropy by forming such intermolecular bonds, so which happens basically at higher densities. So if you look at the equilibrium snapshots of the system in random and symmetric case, clearly there is more aggregation of a given type of reactive monomers in the symmetric case because of their very arrangement basically. So they can form crosslinks at shorter contour distances, as I showed just before. So this is also evident in the GFR profiles, radial density distribution profiles. You can see, okay, I have given many plots, but so if you look at, let's focus on AA intra. So the intramolecular, symmetric case, let's focus on cyan and blue curves basically. So you can see in the symmetric case, there is a secondary peak coming up because of this enhanced correlations. So this has direct consequences on the viscoelasticity of the networks. Although I have not shown, we have seen that in the symmetric case, stress relaxes faster simply because the reactive monomers are able to see each other at shorter distances and they can exchange the bonds faster as compared to the random case. So to summarize, we can tune the internal morphology of the single chain nanoparticle by choosing different solvents, basically solvating in selective versus a good solvent. We can tune its internal architecture, and simply by playing around with the composition as well as the distribution of the reactive monomers, we can get compact versus extended conformations. So just a teaser of what we are doing currently. So so I have told you the results for a dual cross-linking, but you can have multi cross-linking also. So this is also like a modal system for multi-stimuli responsive systems. Like imagine a protein where you have different interactions sitting in. So that can also be modeled using this single chain nanoparticle system. So in this work, what is basically found is that if you increase these different types of reactive monomers, the kind of structures you get are more compactified simply because of the same contour distance logic. So they need to find their partners at longer distances, so they fold more effectively as compared to the homo cross-linking case. If you look at their phase behavior, so these are the equation of state diagrams basically for all A, AB, ABCD, and you can see that pressure is negative in these two cases. That means there is attractions simply coming due to combinatorial entropy, which I have shown before. So if you are interested, you can have a look at this paper. But what I want to drive home from this slide is that there are attractions between the polymer chains in these two cases. So if you were to do a direct coexistence simulations of having a gas and liquid kind of systems, so in A case, they basically demix, okay? But they basically mix, but in these two cases, they remain in different phases. So this model can be used to kind of understand liquid gas phase separation, which has been done here. So what I'm currently doing with a master's student is to look at signatures of liquid-liquid phase separation in such systems. So we are currently doing some basic validations of the model that we have chosen, and this is where we are at. So I can roughly tell you what we have right now. So these red beads are hydrophilic and blue are hydrophobic. So this is how the system looks like. So we have a system of 1000 polymer chains, each of 20 monomers, and we can tune the fraction of hydrophobic beads. So as you increase this hydrophobic beads, so what I'm showing you here is the distribution of the sizes of the chains, histogram of the RG basically. So the peak shifts to lower RGs. So that means as you increase the fraction of hydrophobicity, you are forming more and more compact single chain nanoparticles. So that is coming in because of the increased correlations. You can also see the GFR profiles for the hydrophobic monomers here. So in F is equal to 1, they are structured very well as compared to the other cases. So we are trying to understand this better. So our idea is to first validate our model with a single phase simulations like this, and then kind of do direct coexistence simulations of different liquids and see if there are any signatures of LLPS. So that is where we are at, and I end by thanking my collaborators. So the first two works have been done in collaboration with, so it was my postdoc work while I was at CFM San Sebastian, Spain. So he was my supervisor, and the experimental work has been done by Professor Jose Pomposo and Davide Arena. So we used to call this problem as TGB problem. So the good burger, that's the TGB. So because the problem literally originated when we were having a discussion over lunch at TGB. So we used to call it that way. So currently for the LLPS signatures, I'm working with a master student, Parvati TA at VIT Vellore. And I'll be happy to take any questions.
Yeah, so questions? So, a nice talk. I just want to know that when you are switching the bonds, are you considering any Monte Carlo type enhanced variable, or it is just one?
No, it's coming in completely from the energy. So let me show you the slide. So if you look at this, the three-body interaction term, it is exactly like this. So there is clearly a repulsive interaction if you are beyond 1 sigma. So because the energy is repulsive, the system wants to minimize the energy, and in that process, it makes this bond swap, as simple as that. So you can now actually look at the bond correlation function, and it decays with time, basically.
It's not a physical bond, it's not like continuous force field.
It is like a reversible interaction. Yeah, it's not a physical bond. Yeah, it's a kind of LJ, you can say, the bond interaction.
So in the cross-linking, you said about dissociative and associative. So in your results, like in your MD results, like how can you, I mean, are you sure whether it is actually dissociative, like kind of with tremors?
Okay, so you're talking about this coarse grain part or the atomistic simulations?
The coarse grain.
So coarse grain part, so if you look at the, so in Vitrimer basically, okay, maybe I have that slide. If you look at the stress relaxation profile, okay, I do not have it here. Yes, so if you look at the stress relaxation profile of these networks of Vitrimers, they have two relaxations, okay? So there is a plateau regime here, and then it kind of relaxes. So this is a signature of having a transient polymer network. So that is a signature that we have a Vitrimer-like system, basically.
And so for dissociative, we usually say like the density has to be constant, right? After some point of time, after some crosslinks. Have you seen such the constant density in your simulation?
Okay, so for associative, the cross-linking density is constant. So indeed it is constant. So I have not shown you, but if you plot the total number of reversible bonds as a function of time, it kind of saturates after some time of the simulation and remains there. Yeah.
So so maybe one more question.
Switch the solvent from water to THF.
Right.
And you said you get the globular kind of a structure.
Yes.
So is that process is it reversible?
Okay, so
when you just add water, I mean, can you just reverse that process?
Yes, it should be reversible. That's what I believe.
So, but I mean, just a question is actually, if you think about the drug delivery or something in anything, it should be from the aqueous solution. So when you are bringing this back, I mean, to the water, I think then you will be losing the globular structure, right?
Yeah.
So have you thought of that? I mean, because you need the globular structure for the delivery system, but as soon as you bring that back to water,
Right.
may not have the globular structure.
Yeah.
So
Yeah, so that's a good point. So I think having cross links is a way to stabilize this globular structure. So that is clearly the case, because if you look at this form factor exponents, probably we should do, like you said, the reversible simulations also. I mean, taking the structure in THF and then resolvating in water and see if there are any changes in the structure. But right now, if in H2O, when you transfer it to THF, the form factor exponents are not very different. So it is maintaining the globularity, but it is swelling while maintaining the globularity. So that's what we think is happening. So probably, like you said, we will do the simulations back and see whether there is any change in the internal structure. So, but right now I think we have that signature. It is maintaining the globularity.